Does this stuff agree with that? That's the question I'm sure you're asking yourself. Can we get that from this? We'll be able to, yes? Yeah, which one of these are we going to use? The bottom one. Okay? Now, watch this. Watch, watch. I cancel the satellite mass. It's gone. Boom, roasted. Right? I know that's a joke. Okay. Then I take the r squared and I put it up there and it's like that, yeah? And then what do we have to do? I guess I have to get the 4 pi squared out of there. Yeah? Doesn't that look a lot like Kepler's law? R to the third over t squared. Yes, what's on this side? Isn't everything on this side a constant except what? The mass of the central body. Now, what do Mars, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, all of the planets that existed at this time, right? Okay, because they hadn't made Uranus and Neptune and Pluto yet, right? Okay. They had not yet been formed from the gas clouds. Either that or we didn't have telescopes that were good enough to see them, right? I think that was it. It was a telescope thing, right? Okay. But all the planets, what do all those planets share? They all orbit the sun. So don't they all have the same MC? Therefore, all of their r to the thirds over t squareds are all the same. Isn't that beautiful? That's beautiful. This is not how Kepler came up with it, though. Okay? Newton came up with this whole idea much later, right? And then came back and said, oh yeah, it also agrees with Kepler, because if it doesn't, it can't be right. Okay? Because of aliens, because of the, yeah. Actually, aliens showed Kepler how to do that. That's where it came from. So let's do an example. Let me show you how to use this to solve problems. There's like a little genre of problems that involve Kepler's laws, right? And so all we do is, like for example, Mars is 1.524 AUs, that's what it says, right? From the sun. What does that mean? What's an AU? Astronomical unit. Now, how far are we from the sun in astronomical units? 1, because that's what an astronomical unit means, right? Okay, it means the distance, the Earth-Sun distance, right? Now, we didn't know how far the Earth was from the sun in feet or meters or anything like that until much later, okay? So, but we did know relatively that Mars was farther. It was about 50% farther from the sun than we were, right? We knew that relative sort of thing. Okay, and then we know our year. We knew that period there, right? So how many Earth days is Mars's year? Well, you set the thing up, right? R1 is 1.524 AUs, right? R2 is the Earth, and D2, no, just kidding, right? Okay, AUs. And then the period of Mars, that's the thing that we don't know, right? And then the period of Earth's orbit is 365.26, right? So what you do is you just set this guy up like this. Okay, so you go 1.524 to the third over T1 squared, right? Equals 1.00 to the third over 365.26 squared. And then this is the only thing we don't know. So take your calculators and see if you can calculate what T1 is, right? Just do it on your calculator. We'll do another one that you can do. Now it should be, by the way, a longer period. So if you're getting a shorter period than 365.26, abort, go back. Don't pick on Taryn. She's dangerous. Do you guys have like 670? Oh, I did the same thing I did before. I'm so dyslexic. I typed in 356. Let's try it again. It's the same number, isn't it? Yeah, 687 point. You guys get 687 days? Is that better? I'm such a spaz. I did that 2 times. What does that mean? You want to go to the bathroom? Yeah. Yeah. Si se puede. Only that's like we can, isn't it? I don't know. Can everybody get 687?
Oh, yeah. No, I got like 2.
You got 2. All right.
It's okay. Square root it.
Is he? Here's what I did. I did square root. Here's what I did. Yeah, you got it. This is what I did. Obviously, you can leave off the 1 cubed. Yeah? You probably don't need to put that in there. If you don't cube it,